So last time we talked about empirical risk minimization with RKHS regularization, and the point was that if you have a loss function that only depends on the values of the function at a set of points, x1 up to xn, and then there's this penalty, which is an increasing function of the Hilbert or RKHS norm, then the solution has to be in this finite dimensional subspace, the span of the kernel functions anchored at x1 up to xn. And then once you have it, you can, so solution would be of this form, f alpha, where this 1 over root n is for convenience because of the way you define the kernel matrix. And so if you do this, you can calculate the Hilbert norm. The Hilbert norm is scored with the alpha transpose k alpha. And then f evaluated, f alpha evaluated xj would be basically the jth element of this matrix product, matrix vector product k alpha j, and then you plug it in, multiply by root n, and this would give you a finite dimensional problem. In particular, if you do it for the kernel ridge regression, once you try to solve that, there's a simple solution, which is given here, alpha hat. And so once you have the alpha hat, you can plug it into this, you get a full functional estimator. And you can do the same with the hinge loss. The problem then won't be, there won't be a closed form solution, but you can reduce it to a finite dimensional problem. If you do that, and then you form the dual, you can see that that's basically the dual of the soft SVM if you replace the inner products with the kernel function, with the kernel trick. So the kernel trick in like the dual of the soft SVM basically corresponds to solving this infinite dimensional problem in this primal case. And so that would be the kernel SVM, and then you can solve it in many different ways. Okay, so then we moved on to talk a little bit about, so what I want to do is basically talk a little bit about error bounds. Well, before doing that, we have this nice representation. We're building towards this representation of an RKHS in terms of the eigenfunctions of the corresponding kernel integral operator. So, so let's keep these definitions in mind. Kernel matrix or kernel function is called the Mercer kernel if the underlying space X is a compact metric space. So compact metric space. It might be even like possible to be like Hausdorff topological space, compact Hausdorff topological space, but compact metric space is good enough. And then the kernel is continuous and PSD. That's a Mercer kernel. So the domain is compact, the kernel is continuous, PSD is, any kernel has to be PSD by definition. Then for these kernels, like the RKHSs, we know a lot. So for example, we know that the RKHS has to be separable. It has a countable orthonormal basis, for example. And we wanted to like find a good orthonormal basis. We started with some, forget about this, we started with some sort of more refined discussion. I'm not going to go over this again, but if, for example, the kernel is in LP, then the RKHS is embedded in LP continuously. There's an adjoint of this embedding, and then together, so the adjoint would be basically this integral operator that maps from, let's say in the case of L2, the dual would be L2 again. So you map from L2 back to H, and then the composition of these operators is basically the kernel integral operator that maps L2 to L2, and because it's a self-adjoint positive and compact operator, we didn't talk about compactness, but you actually can show that under these conditions, it would be a Hilbert-Schmidt operator, which is a smaller class than compact operators. So TK is a Hilbert-Schmidt operator. Self-adjoint, the key is that self-adjoint, and then compact, so it has, sorry, self-adjoint and positive, so it has decomposition in terms of like a diagonalization in terms of the eigenfunction. So you have, this is the kernel integral operator, and then you have a bunch of eigenfunctions, phi i's, and a collection of eigenvalues such that this kernel integral operator sort of can be expressed like this. This is you express f in the phi basis, and the action of this operator is basically like a diagonal matrix in that basis. So you rescale these coefficients by mu I. So basically each direction gets multiplied by mu I. That's sort of the usual representation that you get for symmetric matrices, for example. So these phi i's are orthonormal in L2. So they form an orthonormal system, ONS, let's say, in L2. And we also argued that they are orthogonal. Doing some calculations, you can actually show that you can take these to be actually functions in the Hilbert space, like the RKHS as well. So they're not only like equivalence classes, but you can like use actual functions for them. So continuous, let's say, things like this. So it turns out that these eigenfunctions would be orthogonal in the Hilbert space, but they're not orthonormal. So the norm would be 1 over mu I, and then shows that because mu i's are going to 0, it shows that the subsequent functions, eigenfunctions, become, let's say if you think of H as measuring roughness, they become rougher. So the Hilbert norm blows up, while the L2 norm is fixed at 1. Okay, so these are some observations that we made. And so if you rescale these eigenfunctions by root mu I phi I, the norm is also going to be 1. So this would be an orthonormal system for H. One question remains is, for example, is that an orthonormal basis for H? So do they express everything in H? And the answer is that if the kernel is a Mercer kernel, at least that's a sufficient condition. If it's a Mercer kernel, then this would be an orthonormal basis. That's what I want to talk a little bit about. So basically, in that case, everything in the Hilbert space, if you have F in H, then it has an expansion like these in terms of these. This is with an orthonormal basis, so it has an expansion like that. So you can represent every function in the RKHS like that. Okay. Let me talk a little bit about that. So this summarizes the Mercer's result. So if K is a Mercer kernel, and then P, let's say a finite, or like sigma finite, most likely, would be finite, most likely. So finite Borel measure with support X, so X is compact. And then there's this associated kernel integral operator from L2 to L2. Then there's a countable collection of continuous functions, phi j, that are orthonormal in L2. They're eigenfunctions of Tk. The corresponding eigenvalues, they're non-increasing, positive, sequence converging to 0. So this phi j might not be a full orthonormal basis for L2. So they expand basically the range of Tk. And for every f in, so this is the representation we have. This is not difficult, but the key is like this part, which is this is the Mercer's result, that the kernel has an expansion. So that kernel function has an expansion as the sum in terms of these eigenfunctions. And this convergence is uniform and absolute. So it's an absolute and uniform. So it's like the strongest form of convergence that you can think of. So I want to use this to argue that we can represent basically the RKHS as linear combination of these phi's. So under these conditions, if you have basically Mercer's representation of the kernel in terms of these eigenfunctions, then you're done basically. So this is not what I'm going to prove. The proof is not as straightforward, but if you're interested, you can dig up the proof. This part is fine. This is basically, we argue this follows from a spectral theorem for self-adjoint operators. But the fact that the kernel can be written like that is more interesting. So remember, this is an integral operator. This is just a pointwise identity. Okay, so under these conditions, the first thing that we note is if this expansion, for example, holds, if I define a function like this, pointwise, so for every x, this is a series. This series, the first thing to be observed is that converges uniformly, absolutely, if this is true. If beta j is divided by mu j, the sum is finite. So any idea how to like argue this? Suppose I know something like that. Norm of, I mean, what kind of norm? Norm wouldn't be, but I want to show that this converges pointwise, right? As like for every x, this converges, and also like absolutely and uniformly converges. It doesn't matter that it's just pointwise convergence. We have pointwise convergence. So let's say, I'll look at the absolute value basically if you want. Let's say I want to show that the sum converges absolutely pointwise. Like uniform is, you don't have to worry about uniformness. I want to show that this is finite. If this is finite, the series converges absolutely. So like either like pointwise function will define. So in order to show this, I'm going to do this. Beta j divided by root mu j, right? And then root mu j phi x. So mu's are positive. So I'm going to do it like that. So this would be equal to this. Right now, any ideas how to proceed? A good inequality here is Cauchy-Schwarz. So you get this squared divided by mu j, 1/2. And then summation mu j phi x squared phi j. Phi j. Squared. Right, so from Mercer's theorem, we have this, the kxy. This series converges absolutely. So you get mu j phi x phi j from 1 to infinity. This is finite. Also, like the absolute value is finite. So for example, this guy is finite. If I look at x, this would be mu j. This is definitely positive, and this is finite. Okay, so this is finite. This is by assumption finite. So beta j's are a sequence that. So this sum is finite. So the sum converges absolutely. So it's just converges pointwise as well. So this defines a function. Defines a function because the conversion pointwise. Okay, so whenever beta j satisfies this. So then the idea is that I'm going to look at all these functions that look like this, where beta j satisfy this. Okay, and the claim is that this is, when I equip this with this inner product, this is the RKHS of the kernel. So this answers our questions because this shows that these phi j's form a basis for H. And it's easy to see for this inner product that they're basically orthonormal as well with respect to this inner product, right? Because we'll see. So what this is saying is these are in L2. So if f is like that, then it's easy to see that like if x is like beta j phi j, then the inner product of f and let's say phi I, in L2 would be, what would it be? It would basically, I can just, the sum just converges very nicely. So this would be phi I, phi j in L2. And we know that these are orthogonal, right? So actually they're orthonormal in L2. So that would be basically beta I. So this is like, if I have an expansion like this, this would be some beta j, this would be some alpha j, so if I can write f as summation beta j phi j, and then g is summation alpha j phi j, what this is saying is that the inner product is basically alpha j beta j divided by mu j. Okay. And you can also see that phi j itself is so phi j itself is an edge, right? And you can also see that the norm, so the way we define this, the norm of phi j, what will be the Hilbert norm, if this is the Hilbert norm, the way I define it? What will be the norm of phi j? So one of these terms would be like 1 over mu j, and right. So it matches what we sort of had before. So this, like, the L2 norm is 1. The Hilbert norm is 1 over mu j. So how do we show that this is in fact the RKHS? So the first thing to note is like you can verify that this is a valid inner product. This would be Hilbert space, so it's not hard to show that. The next thing to note is that the kernel, so k of x, by Mercer's theorem, it has this representation. Okay, this converges in every conceivable way that you can imagine. This belongs to H. Okay, in order to show that it belongs to H, how should we like argue that this belongs to H? So this is of this form, right? This is from the Mercer's result, right? This is of that form for these being beta j's, right? So this is like beta j. So I just have to verify that summation beta j squared over mu j is finite. Okay, that's what I have to verify. But this is so with beta j being mu j phi j x, this is just summation mu j phi j x squared divided by mu j, j from 1 to infinity. And this is mu j phi j x squared, j from 1 to infinity. Okay, and this is kxx, which we know is finite. Okay, so this shows that, so this verify. Okay, so kx, this belongs to this RKHS, so we like the Hilbert space that we define. The next thing is to show that this has the reproducing property. Okay, so this is 1. But let's say this is 1, this is 2, this is 3. So this is 2, 3. I want to show that because this is in there, so I want to show that this times some f in the Hilbert norm would reproduce f. So suppose f has this expansion, right? You know that this is the case, and then summation alpha j squared. Because f is in the Hilbert space, by definition has to have some expansion like that. So how do we proceed to show that this is reproducing? So we know also that the kernel has this expansion, right? This is the kernel. And this is f, right? From the definition of the inner product, this is just summation j from 1 to infinity, alpha j, beta j divided by mu j. Okay, where alpha is this, beta is that. Right, so this is summation alpha j, mu j, phi jx, right, divided by mu j. Okay, that's the beta here. This goes here. And this sort of simplifies what I get summation alpha j phi jx. It's just by definition f of x. Right, so this reproduces f. So it is, we have Hilbert space. There is this kernel that represents the evaluation. Functional has a reproducing property, basically. And so it has to be an RKHS. And we know that the RKHS of any kernel is unique. We argued that. Right? Remember, there's a one-to-one correspondence. So this has to be the RKHS of the kernel. This shows that this is a representation of the RKHS of the kernel. And it gives you a very nice idea of what these functions look like. Intuitively, what this is saying is there is something subtle. It's so things that for which the beta j is squared. So things that look like this, for which the beta j is squared is finite. These are in L2, right? But for it to be in the RKHS, this has to be finite, which is a stronger condition. So this, for example, implies that beta j. You know that a series converges if, like, a necessary condition is that beta j squared over mu j is O of 1. Right, so this implies that beta j has to be O of root mu j. Mu j's are going to 0, okay, at a certain rate. So this just implies that beta j has to be O of 1. This implies that beta j has to be O of root mu j. So it says that the decay of these coefficients is faster than usual. So if you want, you can say that there is some sort of an alignment between the functions and the eigenfunctions of the kernel operator. So the function has doesn't sort of spread out in the directions of the eigenfunctions. So that dies down fast. So it's concentrated basically more. So if you fix the L2 norm to be 1, compared to a generic function in L2, most of the energy is concentrated near the top eigenfunctions of the kernel. So there's not much you can put on the tails of that. So this is some sort of an interesting observation, which might be a little bit subtle. But that's what these RKHs. So they look like this is if you look at the unit ball, the unit ball would be this less than or equal to 1, because if you think of the so the norm of h f basically. So if f is like that, then the norm of f would be just summation beta j over mu j. So you can see just this is effectively saying all the things for which the Hilbert norm is finite. So this is less than or equal to 1. That would define an ellipsoid in L2. So the unit ball of the Hilbert, the RKHS, looks like an ellipsoid in the L2, and with many directions, sort of very like the spread is very tiny. So it's like, this is like the unit ball. The other one might look like this. So there are directions in which they don't spread much. Okay, questions? So the decay rate of these eigenvalues actually tell you how big the RKHS is, and so effectively like control the error rates. That's the main sort of take-home message that I'm going to talk a little bit about. Questions? No questions. Okay, so here's an example. If you look at the Sobolev kernel that we looked at as like a running example, min st on 0 to 1, you can write down the integral. So the eigenfunctions of the integral operator have to satisfy this. So remember, this is just basically the kernel, which is min st times phi of s ds from 0 to 1. If you integrate it, this has to be mu phi t, right? This would be like an integral from 0 to t. If it's from 0 to t, then the minimum is s. So you get s phi s ds, right? Plus t phi s ds from t to 1. And then you can differentiate. So differentiate twice if I haven't done any mistakes. So that would be like, has to give you something like that. So it gives you a differential equation. And then you like bring out your differential equation scales and try to solve this. And there's this boundary condition, because we had that for the kernel. With that boundary condition, the solutions would look like, there's this boundary condition. Also, this gives you one boundary condition. It's you're like differentiating twice. This, you have to satisfy these two, so it gives you two boundary conditions, and this is a second order equation. So you can solve this. Hopefully, this turns out to be the case. For example, like evaluated at 1. If I said 1 here, I get an equation. So you get boundary condition at 0 and boundary condition at 1. And this would give you, hopefully, the solutions. You get these signs. And you can see they're not, it is easy to verify then. Like as an exercise, you can show that these are orthonormal in L2. But they're not like an orthonormal basis for L2 of 0, 1, because you also need cosines, and so all the frequencies are missing. But this just, it's like, if you haven't done any, if you have like computed all the possible solutions of this by the Mercer theorem, because this is a continuous kernel and compact support, the collection of all the eigenfunctions, which are basically, so this has to be phi j. There's a discrete set of eigenvalues, so j equal, I believe, 1 to up to infinity. So these functions, phi j's, that look like this, they expand the RKHS. Okay, so the linear span of this is the RKHS containing the linear span, and then you have to, not the linear span, but just the, you can write the series expansion, right? The series expansion holds with these phi's for this RKHS. So you can represent every function as a summation of these with coefficients such that the coefficients squared divided by mu j goes to 0. And then this mu j, you can see it's like asymptotically scales like j to the negative 2. Okay, so it polynomially decays with order 2. It's not that fast. So if you look at the Gaussian kernel, the eigenfunctions decay like exponentially fast, like e to the negative j or some constant times j. But this decays polynomially. Higher order Sobolev kernels, this decays faster. But you have like one derivative control. That's what you get. Questions? Okay, this is a good exercise for you to do. Now I want to talk a little bit about error bounds. I'm going to talk about the constrained version of the problem instead of remember I want to provide bounds for the kernel ridge regression. So the kernel ridge regression is argmin 1 over n summation I from 1 to n yi minus fxi squared plus lambda f Hilbert squared. So when you try to prove something about this, we can show that if you take, for example, lambda large enough, then f will have Hilbert norm control, let's say less than some constant. Then the problem sort of reduces to this problem, minimizing this over, this is a ball of RKHS. So this is equivalent to saying H is an H, and the Hilbert norm is controlled by 1. But there is some steps to show that for sufficiently large lambda, this actually happens. So in order to avoid that, I'm just going to analyze this. This is equivalent. So for some lambda, you're solving this effectively. You just have to, in the end, show that lambda, because if you increase lambda, you'd increase the bias. But the amount that you need to increase such that this happens is controlled. It just doesn't include, doesn't add anything else to the bound. So it's absorbed by the other terms. But let's worry about this. So this is saying I'm trying to find a function that sort of closely approximate yi, but the Hilbert norm is controlled by 1. It could be any other constant. For simplicity, I'm doing it 1. You can rescale to make it 1. This prevents the function from varying too much. Okay, so you may not be able to actually satisfy. So this is different than the interpolation problem. So there might not be any h that makes this 0, and the Hilbert norm is less than 1. That's the idea. So the data is assumed to be of this form. I'm going to assume that h star actually belongs to the ball of radius h. So the model is properly specified. So you'd expect that eventually you should be able to, because the h is feasible in this problem. Eventually you should be able to recover it. And then the noise are basically there's the sigma is the noise level, and the wi's are IID drops from 0 to normal 0 to 1. Okay. So one thing is that for this problem, you can actually, not the constrained version, but for this one, actually, you can compute the exact solution, and you can write down the exact error bounds. But the technique that I'm going to work with is more general. So it could work for general loss functions where you don't have closed form. So that's why I'm doing this. For the kernel ridge regression, there are simpler ways of deriving these bounds. Surprisingly, for this one, it would be a little bit more difficult because it's not easy to write down the closed form solution for this. Is the setting clear? So what we want to show is something like h hat, call it n, let's say h hat minus h star in some norm. I'm going to use the empirical norm. This is by definition summation I from 1 to n. H hat of xi minus h star of xi squared. Okay. I want to show that this is up to constant, sort of small. This approximates the L2 norm when n gets large. If xi's are randomly drawn IID from some distribution on script x, but because we're assuming xi's to be non-random, this is a good quantity to look at. There's no need to connect it to the actual L2 norm. Another thing that I'm going to use is this operator that I'm going to define. This notation is not standard, but it's helpful. So I'm going to write, Sn of h for the operator that takes h and outputs these the values of h at these points rescaled by 1/. So for example, the norm SNH, the L2 norm of this, the usual L2 norm is just going to be the empirical norm in the sense that I have defined above. Okay. So this is nothing but the L2 norm of this image of h under this linear, it's a linear transformation. Okay, and then I'm defining this so-called local Gaussian complexity. So we look at this guy SNH, inner product with W. W is the noise vector here. So W is W1, W2, Wn. So this is measuring the inner product. The absolute is supremum over these two sets. And then I'm taking an expectation. So if you compare this with Rademacher complexity that we have seen before, this is very similar, but with the so before we had like epsilon here, and epsilon had like independent Rademacher variables. Now we're taking like Gaussian entries for this vector. So it serves the same purpose. Okay, so it measures some sort of a average width of the set in different directions. Actually, if it wasn't the absolute value wasn't there, it would be actually called a Gaussian width. So it's local because you could have like worked with supremum. This just translates things to the finite dimensional domain. I could have worked with this. That would be basically sort of a Gaussian width or Gaussian complexity of the Hilbert ball. But I'm also assuming that I'm in the neighborhood, like the L2 neighborhood of radius delta. That's where interesting things happen. And for this reason, it's called the local Gaussian complexity. The effective thing is that I want to look at basically, you'll see the neighborhood of HS star actually. So so what we can think of this as, you'll see in the proof that what we basically do is you want to control H minus HS star, assuming that the L2 norm of this is bounded by delta, and H minus HS star is basically is going to be in the twice the Hilbert ball. If H is in the Hilbert ball, because HS star is in the Hilbert ball, this would be in the twice this. So basically what we're doing is we're controlling these deviations. That's what I want to do, but it's easier to write just everything as this. You'll see in the proof. The locality comes from this part. It's a little bit hard to explain, but once you go through the proof, you understand why this matters. So this quantity tells you something about Hilbert space. Once you compute it, it also depends on the x1 up to xn. But we're going to give you a result for this. So suppose you have this, then if delta n is the smallest solution of this equation, then if h hat n is the constrained estimator of this defined here, let's say hn, that's the hn, then the empirical norm of hn minus h star is controlled by this delta n plus sigma over root n t with this much probability. And it's easy then to show that the expectation would be, because of this tail bound, would be delta n squared plus sigma squared over n. And generally this term, this is the parametric rate, this would be larger. And so this would dominate. So what this result is saying is that this so-called critical radius, the solution of this, the smallest solution basically controls the rate. This gives you a very nice way of easily like calculating the rate for any RKHS. Whether this is the best possible is not something that we don't talk about, but like in the case of the Sobolev one, for example, it gives you the optimal rate. It can be better than this. So is there like the statement here. Okay, so let's see where this comes from. No, actually, okay. Let me show you how we can get a like concrete result. So if you look at the kernel matrix, this is the next result. If you look at the kernel matrix, which is, if you recall, defined like this, it's a matrix whose ijth entry is k of xij divided by n, and let mu hat 1 up to mu hat n be the eigenvalues of this kernel matrix. These eigenvalues, as n grows, converge to the eigenvalues of the integral operator, the mu's that we had. This is like another set of results which we don't talk about. But generally speaking, you expect, that's why we do the normalization. Okay, so if you don't normalize, the eigenvalues blow up. But if you normalize, the eigenvalues of k stabilize, they converge to the eigenvalues of the kernel integral operator. So for example, the decay of this would be like j to the -2 roughly for the Sobolev one. And then these eigenvalues, let's call them like the empirical eigenvalues. So call them empirical eigenvalues expected to converge to mu j. We can call them population version, mu j, the eigenvalues of the kernel integral operator, kk. But then that Gaussian complexity is controlled by something like this, √2 min delta squared mu hat I. So it just depends on how fast these decay. So to see how this is useful, consider the case that mu hat j decays like this. So this is what this notation means. Mu hat I is like there is a constant such that this is less than this, and there's another constant such that this is like sandwiched between like constant multiples of this. For example, for the Sobolev kernel, you expect alpha to be 2 here. Okay, so then I would have something like this. I want to see where the minimum occurs. So delta squared, let's say, equal to this roughly. This means I has to be delta to the -2 over alpha, right? So let's say this is an integer for simplicity, and then call this k, right? And call this k. So you see that from I from 1 to k, basically the minimum would be delta squared, right? And then I is k plus from k plus 1 to n. Yeah, so as n grows, like I to the negative alpha gets smaller, so eventually this takes over, so you get I minus alpha. Right, so this gives me k, this gives me exactly this. K delta squared plus that. Okay, then this term can be bounded of 2 constants. Actually, it can be bounded exactly, I believe, by k from 1 to n. Let's do it to infinity. X to the negative alpha dx. Right, so you know these, if you have a function like that, you're sort of, this is, let's say, gi. So it's like you can think of it a continuous function, you're sort of summing right, you know this, right? You can approximate these sums by integrals. So basically approximate the integrals by the sum, but that gives you an inequality. So if something like that, if I have a function like this, say, so this would be like g of 1. This would be g of 2, g of 3. If I'm trying to sum g1, g2, g3, say this is K, sort of. This is G, K plus 1, G, K plus 2, K plus 3. And then there is the GK here, right? So this is like, there's the one, here's, so this is, okay. This is bad. This is K plus 1, this is K plus 2, K plus 3. This is GK plus 1, right? GK plus 2, GK plus 3. So when I add GK plus 1, I'm basically adding GK plus 1 times the length here is 1, right? So I'm adding this plus that, right? So the integral from K to infinity of this function is an upper bound on this sum, right? And then I can calculate this. That's basically what I have here. This is going to be negative 1 over alpha plus 1. So alpha is bigger than 1. X to the negative alpha plus 1 from K to infinity, that would give me 1 minus alpha minus 1, K to the negative alpha plus 1. Right, and I absorb the 1 or alpha into constant, so this is basically K to the negative alpha plus 1. Okay, so in the end, the first term is K delta, the second term is K to the negative alpha plus 1. And I also know that K is delta negative 2 over alpha. So you plug that in, this and then this, and then you can see that the two terms are basically the same, right? So this is delta to the 2 minus 2 over alpha. If you multiply out the second term, the exponent would be 2 minus 2 over alpha. Okay, so it's like twice this, again, bounded by constant times this. So that's our where is it? Okay, so that's our bound on. So what this result is saying is that G delta sort of is bounded up to constants, right? Ignoring the constant. So G delta is bounded by this because there's this, I have to take the square root, right? Taking the square root of this, that would give me that from the result, right? So then the critical inequality, that's this result. I have to solve this equation. So the critical inequality gives me sigma root n. I want the smallest solution of this. Well, basically any solution of this would work up to constants. I can replace this with an upper bound. So any solution of this would definitely satisfy this. So that would be good enough for me. So I'm going to solve this. You can see it gives you an equation for delta. If we solve this, it would give me sigma over root n. One of the deltas cancel out, so this cancels with that. I get delta 1 plus 1 over alpha. Okay, and then this gives me sigma over root n to the alpha over alpha plus 1. This is saying delta n. This is saying delta has to be bigger than or equal to this, right? And I want the smallest delta, so I'm going to push it to this. So what this is saying is that the smallest delta has to be, can be like at most this, right? This is saying any delta that satisfies this. So the end result is that delta n is at most this. You can just take it to be this. Okay? And this is just, if I square this, put a square on this, I'm just going to square this. So that would give me, this is like delta squared. So expectation h hat minus h star n would be like delta n squared plus sigma squared over n. From that result, this is up to constants bounded by sigma squared over n alpha or alpha plus 1. I'm just taking the square of this. right? Plus sigma squared over n. But this dominates because this is slower, and it goes to 0 slower, so that would be like bounded by sigma squared over n, alpha or alpha plus 1. So that shows that the rate at which you can estimate for the class for which this decays like that is this. So for example, if alpha is equal to 2, then you would get, that's the Sobolev kernel, the rate would be sigma squared over n to the 2/3. Right, which is slower than, and this is actually optimal for that class. So the minimax rate over that class is 2 over 10. The parametric rate is sigma squared over n, okay, which is much faster than this. You can imagine as n grows, in order to like make the error like half, cause it to like reduce by half, you have to pay a lot more samples, right? Asymptotically, you can see like multiplying by, let's say, 10 reduces the error by 1 over 10, but here would be like 1 over 10 to the 2 over 3rd, which is smaller. So you need a lot more samples to be able to estimate a generic function in the wall of the RKHS. And you can see as alpha gets larger, this approaches sigma squared over 1, sigma squared over n, which is the parametric rate. So if you have like larger alpha, these eigenvalues decay faster. So the RKHS is smaller. Okay, so it penalizes the like high frequency eigenfunctions much severely. So that is reflected in the rate. Okay, sounds good. So this gives you a very nice sort of idea of how the machinery of RKHS sort of eigen decompositions and these Mercer's sort of theorem, these things sort of connect to statistical performance. So let's try to prove these. The more difficult one is just this result. So if you've taken like 200C with me, the technique is very similar to what we use there for non-parametric regression. It's just, I'm going to basically repeat that. So optimality condition gives you this basic inequality, right? So the h hat is the optimal solution, h star is the feasible solution. And I'm going to plug in the yi, right? So yi is h star xi plus, there should be a sigma here, missing, sigma wi. And the same goes here, right? What I would get is, and then define this delta, the difference between h hat and h star. Delta hat is that. So this gives me basically sigma wi minus delta hat xi, right? And this gives me sigma wi. Right, and then you square this term, like the square of this goes away. This goes away with one of these terms. I get the delta hat xi squared, so that's what I'm keeping here. So the square of this will give me this, and then I get twice this times that. I move it to the other side, that will give me this term. Okay, and the square of this cancels with the square of this. So it gives me this basic inequality. I'm going to write it for simplicity as, this is definitely the empirical norm squared. This one for simplicity, I'm going to write as basically 2 over sigma root n, and then put 1 over root n here. So this quantity, 1 over root n, summation I from 1 to n, delta hat xi and wi, that I'm representing as, for simplicity, as delta hat wn. Okay, this is really the inner product, if you want, properly, that Sn, delta hat, and w. This is the L2 usual inner product. In order to not write that Sn, I'm just writing it like that. Okay, so we have this nice little inequality, basic inequality, and the general idea is to show that delta hat is in a good set, because the controlling this term, as if you've seen again any of these arguments, this is hard because delta hat n depends on W. Because it just depends on h hat is like, depends on yi depends on W. So this is a random term, like doubly random, because both terms are random and they're dependent on each other. So controlling this is difficult usually, so we resort, so the difficulty is that delta hat and W are dependent random variables. So we resort like solution, resort to uniform bounds on like delta maps to this. So if I can control like this function generally for any delta in some set, and then delta hat happens to be in that set, then I have a good control. So in order to just make this work, we need to have like a good set for delta hat, small enough. And so we observe here that because this is h hat minus h, and both of them are assumed to be in the h star, both of them are in the ball of radius 1 in the Hilbert space. The difference is in a ball of radius 2, right? So that's the structure equation that we have. And this is good enough for us. What I'm going to do is I'm going to assume that also like this is the tricky part. I would like to also assume that this is less than delta. This is not going to be less than delta, but like for now, bear with me. Just assume that you can also like assume that the empirical norm of this is less than delta. Okay. So what I'm going to do is that, and then this 2 later on we can absorb, right? So this being in the ball radius 2, or so I could have defined this as 2, but for simplicity, I'm just defining it like this. So if I multiply by, if I replace the delta by, yeah, I'll forget about it. We'll take out the 2. Okay. So basically 1/2 delta hat belongs to ball of radius h. Okay, that's good enough. So I'm going to look at this function. This is a random function of delta, and the first thing, this is the result that I also use in 200C. If BH, if this set that you're optimizing over is star-shaped, which is definitely star-shaped because this is a ball, so you know star-shaped means if I connect any point to the origin, everything in between is in the set. The BH is convex, so definitely star-shaped, but this result holds for any star-shaped set. So this bound holds. If I define f delta like that, then I can remove this constraint on the empirical norm, so this would hold for any delta in the ball of radius h. We'll come back to this, so that's how I can get rid of this. But this allows me to control this supremum better. So when I put a delta there, this is going to at most be like proportional to delta. Whereas if I don't do it, this doesn't depend on delta. So this is like a local complexity of the ball, not the general complexity of the ball. And you can see like the local. So the way that this cuts into this ball gives you this minimum and delta squared and mu j. If I don't include it, I get a much bigger bound. So you'll see like, but I can remove this locality by this result. Once I have control like this, then this is going to be controls for any delta in BH by this. We'll come back to this if you want, but it's easy to show that once BH is a star shape, if I have something like that, then I have this. So for now, let's believe this. Then I know that delta hat over 2 belongs to the ball. So I can apply this equation or sorry, this inequality to delta hat over 2. And what I get is this divided by basically 4, and I multiply 4, both sides by 4, so I get some equation like that. Okay, and then from this, I conclude a result like this. And the way to see this is I consider the two cases separately. So if this is the maximum, right, I would get, so let's say delta hat n divided by, this is bigger than or equal to 1, then I get delta hat n squared less than or equal to 4 sigma delta hat n divided by delta f delta. So that would simplify, this goes away with that. So I get 4 sigma, so I get this. Oh, there is a sigma tilde here. What is sigma tilde? So sigma tilde is, this is sigma tilde. Okay. Oh, I forgot to mention. Okay, so what we get here is, so what I'm doing is combine this basically with basic inequality, right? So this is less than or equal to 2 sigma tilde delta hat n w, right? That's what I'm doing here. And I also know that delta hat divided by 2 wn from that result above is less than the max. Delta hat n divided by 2 over delta and then 1 times f delta. I should probably do this somewhere else. It seems like the constants are off a little bit. Okay, what I'm doing is this is the basic inequality. So this is the basic inequality that we had. And then I'm going to apply that delta, this result to delta hat n, delta hat over 2. So I get this. I also get delta hat over 2n divided by delta n1 f delta. Right? So what do I get? This gives me delta hat wn less than, I'm going to multiply by 2 everywhere, right? And then this would be like delta hat and then 2. I'm going to like bound this by 2 times that. So right? So it seems to me that we can replace, so then if I combine these two, I get delta hat n squared is less than or equal to, I actually get 4, which is nice. 4 sigma. Yeah, I don't know how I did it earlier, but this also works, seems to be like correct, right? That's how you get that bound. Just combine the basic inequality with this. Sigma tilde is sigma over root n. So I get this inequality. And then what I'm doing here, like separately considering the two cases, once I consider this case, I would get that delta hat n is controlled by 4 sigma tilde f delta divided by delta, that's this first term. And then the other case is where delta hat n, this is less than 1, should be n here. then the dominant term would be less than, the dominant term would be 1. So you get delta hat n squared less than 4 this times f delta, right? And then you take the square root. You get root for sigma f delta. So you can say that these two terms basically give you these two terms. Okay, so that's bounded by the maximum of the two, right? So you have this nice bound. It just like you managed to control this. This is bounded by what you have an idea how to control this. This random quantity. How do we like generally work with these things? So generally what you do is like you first try to control the expectation and ensure that this is concentrated near the expectation. That's the basic idea. So because we don't have time, I'm going to be a little bit quick here. So what you're going to do is that you note that f delta is a Lipschitz function of W. So it's a delta Lipschitz function of this W. W is a Gaussian vector. This is a Lipschitz function of a Gaussian vector. And there are very powerful results for concentration of Lipschitz functions of Gaussian distribution. So this concentrates near its expectation, and the concentration is sort of dimension-free. Basically, this is going to be sub-Gaussian. It's sub-Gaussian norm delta. That follows from sub-Gaussian concentration. We didn't talk about this in this course, but take any book on concentration inequality. This is there. So this is a delta Lipschitz function of W, hence by Gaussian concentration, you get this bound. So f delta is at most expectation plus t delta with this probability. So delta would be an upper bound of the sub-Gaussian norm, or the sub-Gaussian standard of the supremum. So this expectation, by definition, if you go back, is just G delta that we define. So the expectation of this is that Gaussian complexity. So what I get is that with this same probability, I just replace f delta with this. This is now G delta plus T delta. And then that's basically this bound. I replace f delta here with the expectation plus T delta. And then this is the assumption that we had. So remember the sigma tilde is just sigma over root n. So that's the critical inequality. We assume that delta satisfies this. Under this assumption, this quantity is bounded by, the first term is going to be bounded by sigma squared. The second term is this. Factor out 1 delta, and then this is further bounded by that. So if you look at this, both this is going to be bounded by this guy. And this is also going to be bounded by the square root of this, which is the same thing. So both terms will be bounded by that. So that's the end result that you prove. So if you go back to like what we wanted, this is basically what we showed is that any solution of this basically will satisfy this. And so you take the smallest solution. Again, then the expectation follows by integrating. It's just directly follows from that. What remains is there's the proof of the other result. I'm going to maybe come back and talk a little bit about that next time. And depending on how much time we have, I might start talking a little bit about bandit problems, but that would be like our last lecture. And then the lecture after that, you guys take over. Okay. Sounds good? Okay. Thank you, guys. Stop here. We'll continue next time.